So for sets, a set has elements. They are just individuals. They don't really care about other things. It's just there. Just imagine it's like us. When we are young, when we are kids, we only think of ourselves. We don't really, not because we are bad, but we just don't know how to think in other people's situation. We just think just for us. But when we grow up, we start to think the feelings of other people, right? We need to understand the relations between people. It's like that. In this section, we will learn the relation between objects, not just individual things. Okay? That's basically the philosophy of this chapter. So the first one is section 3.1, the functions. So function is what? We defined this already, I guess, but let me do this again. A function usually denoted by f from x to y. This is what? This is a way of assigning to each element in x exactly one element in y, right? And this x is called domain and y is called codomain. And the range is the set of range or image is the set of f of x's. And in this case, it's called y is called y equals f of x, because we assign exactly one element in y. So that's y of f. In that case, we write y equals f of x. And a function is a range, the range. The range or image of f is the set of this form y, where y equals f of x for some x in the domain. It's not necessarily the whole set y. It may be the whole set, but not necessarily. Sometimes some elements here are not of this form. So function is usually, this is a usual definition of a function. Normally people define a function like this. But we can also consider function as a subset of the Cartesian product of function. So sometimes we will think of this as a subset. Can be considered as a subset. So f, subset of x product y. But not every subset, but this, with property that for every, okay, let me write in a sentence. For every x, there is exactly one y with this condition. X comma y is in f. Okay? So for every x, f is a subset. So it consists of pairs, x comma y. But for every x, there is exactly one y such that x comma y is in our subset f. And that's basically equivalent definition to this. Function is like this in the traditional way, or also we will consider as a subset. Let me give you an example that will be helpful. X equals 1, 2, 3. Y equals a, b, c. A function, usually we draw a function using diagrams. So 1, 2, 3, a, b, c. So let's say it goes like that, something like that. This is a function. F of 1, this means f of 1 equals a, f of 2 equals c, f of 3 equals a. So for to every element x, element in x, we assign one element. So for 1, we assign, to 1, we assign a. To 2, we assign c. To 3, we assign a. So that's one way of assigning elements there. So f is like that, but f is also, what I said earlier is like this. F is a subset of x times y, x product y. So that means 1 comma a. In other words, x comma f of x will be f as a subset. Right? So let me write this over here. Then because of this, f can be considered as a set of pairs like 1 comma a, 2 comma c, and 3 comma b. And you can see for every element 1 in x, 1 or 2 or 3, there is exactly one y such that x comma y is in f, right? Here, exactly one element. We have exactly one pair like 1 comma something, and exactly one pair 2 comma something, exactly one pair 3 comma something. So it is a function. So it is a function from x to y. So not every subset of x times y is a function. It is called a function if it satisfies the condition that I mentioned. Is this clear? Let me give you some examples that are not functions, just to make it even more clear. X, y, 1, so 1, 2, 3, so a, b, c. For instance, like this. So here, f is what? Is a subset, 1 comma a, 2 comma b. This is not a function. Why? We don't have 3 comma something here. 3 comma something is missing. Another example that's not a function. 1, 2, 3, a, b, c, like this. So as a subset, we can write 1 comma a, 1 comma b. We can always write a diagram as a function, as a subset like this. This is not a function. Why? Because we have two pairs starting with 1. We don't want that. So these are not functions. But otherwise, for every x there is one x comma y, then that's a function. All right? And then we studied functions a lot in calculus, and we considered graphs of them. If this is a function with the domain, codomain, subset of the real numbers, then the graph of, what is the graph of f? Is the set of points. X comma f of x in R times R, right? So example like y equals f of x. This f of x equals x squared. This we put all the points satisfying this condition. Y equals x comma y. Now y equals x squared. So this is the graph of this function, and of course here the domain and codomain are both the real numbers. But we may have a finite set for domain and codomain. And same function, right? X equals x squared. this is still a function from, oh no, this is not a function, from here to there. I'm going to use a different one. I'm going to just construct one. f1 equals 1, f2 equals 1, f3 equals 3, then 2. Then this is a function from x to y. Now what is the graph of this function? So we have 1, 1, 2, 3, 1, 2, 3. So 1, 1. So we put a point here, 1, 1. Let me use this, 1, 1, 2, 1, 3, 2. So this is the graph of this function. Okay. You just put the dots there. There are many functions, of course. We will see many functions. Some functions are important, so they have some name. So definition: if n and m are integers, and m is positive, then what? N mod m is the remainder of n when divided by m. Okay, so this is the remainder. In other words, if n equals mq plus r, where r is, everything is integer, m, then what is n mod m? The remainder, r. And we can show that there is always a unique remainder. So example 7 mod 3, what's that? 1. Minus 2 mod 5? Not minus 2, because the remainder must be always non-negative. So it's going to be 3, because minus 2 equals minus 1 times 5 plus 3, where 3 is in the right range, 0 to 5. I don't know, 2017 mod 10. What's that? 7, right? Etc. And maybe one more. 15 mod 3. 0. What about 5 mod 0? We don't do that. It's not defined. Must be greater than 0. We don't consider this. What about 0 mod 5? This is fine. This is 0. This is not defined. We don't never consider like this, something like this. And we will define more functions. And actually we define this, I guess, or this is the floor. We read this as floor of x, and it's the largest integer less than or equal to x. And similarly, this is the ceiling of x, and is defined to be the smallest integer greater than or equal to x. So we saw like 3.2 equals 3, and minus 3.2 equals minus 4, and 3.2 ceiling equals 4, ceiling of minus 3.2 equals minus 3, etc. Right? And if this is an integer, like 0 is 0. 2017, ceiling 2017. And you can, so this is a function. This is a function, right? Function from x to y. I'm sorry, from r to r. if you say f of x to be the floor of x, then f is a function from R to R. So what is the graph of this? Let me try to draw y equals graph y equals ceiling of x or floor of x first. It takes always integer values, right? So must be integers, right? Like that. But x can be real numbers, and y, the value of y is always integer. So here, when x is an integer, y is x. So it must be in the diagonal line like this. When x is an integer, it must be like that. When x is greater than 0, less than 1, it must be 0. So we have this, but this is excluded. So the graph looks like this. Meaning this solid dot means is included. This empty dot means is excluded. So here, similarly, we have goes like this, in this way. Okay? Maybe similarly, we can draw the function y equals ceiling of x. Again, let me use red. Again, when x is an integer, it's the same, y equals x. And when x is, say, between 0 and 1, what is the value of ceiling? It's ceiling. It must be 1, right? So it's like this. And here, 1 to 2, it's always 2. So it's like this. It's slightly different. Goes like that. This is the graph of the function y equals the ceiling of x. Okay. And so functions. Another definition. F is a function. We say that it's one-to-one or onto. F is one-to-one or injective. They mean the same. Injective. If for every y in the codomain there is at most one x with this condition, f of x equals y. There could be nothing, or if there is, it must be one, only one. You cannot have two or more x satisfying this. So equivalently, in other words, if f of x1 equals f of x2, they cannot be different. Then we must have x1 equals x2, because otherwise we have two values of x such that f of x equals y. Example. Fn equals n2n plus 1. Is this one-to-one? It is one-to-one. It's a one-to-one function, right? Because if fn equals fm, what happens? 2n plus 1 equals 2m plus 1. If you solve this, we get m equals n. So it's one-to-one. It satisfies this condition. Okay? But fn equals 2 to the n minus n squared. This is not one-to-one. Because what is f of 2? 2 squared minus 2 squared, 0. F of 4, 2 to the 4th minus 4 squared is still 0. We have two values of x, such that f of x the f value are the same. It's not one-to-one. All right? And we also define surjective or onto function. F y is a function is called onto or surjective if for every y in the codomain there is at least one x with the condition f of x equals y. So in other words, it means codomain equals range. Range equals codomain. It's the same. It has the same meaning. So everything, if you have x and y, everything here must be mapped by this function. No matter what point you pick in this codomain, there must be an arrow pointing to that point. That's what onto means. So, for example, f of n equals 2n plus 1. Is this an onto function? Is this onto or not onto? Yeah, it depends. Depends on what x and y, the range, what the domain and codomain are. Let me say it's a function from z to z. Is this an onto function? It's not. It's not onto. Because f n can never be 0, right? For all n. If this is onto function, there must be some integer n such that f of n equals 0, because 0 is an element here. 0 is an even number, but fn is always odd, so you cannot have f of n equals 0. So it's not onto. But of course, if you think of this as function from z to, say, even odd integer, then it's an onto function, right? Because for everything here, there is something we have over here. F of n equals that thing. Here is onto. It depends on x and y. If you change the y, maybe you can make this onto. Are these examples okay? So you have to be careful at the range or the codomain. You have to look at the codomain carefully. What about this? Third example. The same function, but R to R. Is this onto or not? Onto? Yes, onto. Because for everything, for every x, you can find this 2n plus 1, right? Because n is x minus 1 over 2 is a real number, so yeah, it's an onto function. So it really depends on the domain and codomain. Any question about these three examples? And all right. So we learned two properties of a function, onto or one-to-one. And if a function has both properties, it's called one-to-one and onto or bijection. This is a bijection if it is one-to-one, one-to-one, and onto at the same time. So example, like this, x, y, 1, 2, 3, a, b, c, like this. one-to-one function, and also onto function, one-to-one onto bijection. If suppose that they are finite sets x and y, and f is a bijection, then what can you say is that if it is a bijection and x, y are finite, then cardinality of x must be equal to the cardinality of y, because this gives us a one-to-one correspondence. One-to-one correspondence. So cardinality must be the same. So bijection is a nice function. It gives us additional information. X equals y. The cardinality of x equals the cardinality of y. And moreover, when we have a bijection, we can talk about its inverse. If f from x to y is a bijection, then the inverse of f is a function, is the function denoted f inverse, and it's from y to x now, such that f inverse of y is defined to be x, where for this. If this, then it's defined, we just reverse. Basically, inverse map just reverses the arrow. So if this is f, what is the inverse? Y, x, x, so a, b, c, just reverse the arrow. 3. So a goes back to 2, so a is, b goes back to 1. And they look really the same here, but usually they don't have to be have to look the same. So f inverse, just reverse the arrow. Inverse function is important. A quick question. Here, we can think of this as a set of pairs, right? 1, b, 2, a, 3, c. And what is the inverse of this? How can you obtain the inverse as a set? What do you do for this? You just flip the coordinate x, y, you just exchange the two numbers in each pair. So it's going to be switch them, b, 1, a, 2, c, 3. So inverse function can be understood like that. You just flip the two coordinates. All right. And now another one. We have a function from x to y and another function from y to z. Then what happens is you can define a new function. The composition of f and g is the function denoted by f circle g. So f circle g, and it is a function from x to z, defined by, so if it's a function for every x, element x in capital X, we must have some element in z. That is defined by this, f of g of x. This is well defined. So the idea here is that, let me give you this base underlying idea here. So G is an assignment of elements from X to Y. So this is G. G is represented by arrows from X to Y, and F is like here. So to be more precise, let's say A, B, C, and X, Y, Z, W. X, Y, Z, W. So I don't know, just I can just make arrows like this, and here, like that, right? So we have two functions. Then we can compose two things. Then this, how is the G, F compose G defined? You just follow the two arrows. So here 4 goes to C and then goes to X. So in this, for this map, we just map this to this directly. And 3 goes to B and then Y, so it's this, right? 2 goes to A and then Y, so it's like this. A goes to B and then Y, so it's like this. So the composition is just following the arrows. Here you have to be careful, how we write this, the order of this. The order is important, right? We write in this way, not G, because here you may think we consider G first and then F, so maybe it may look more natural to write G compose G and G compose F instead of F compose G, right? Because what we really do is we follow G and F, right? But why do we write the opposite way, F compose Y? Because we really want to have an equation like this. Because if you define this backwards, then this would be like F of G of X, which is a little confusing. And that's why we define the order like this, F compose G. So we apply G first to X and then F to the resulting equation. Okay? So we don't define this. But like I said several times, we have freedom to choose our notation. So some authors in other textbooks use this notation. But in our textbook, we will follow this. Okay? So we will use this. Compose. So just remember this. We apply G first and then F. Composition is a very important operation on functions because we can make many functions out of simple functions. Many functions are really, if you remember in calculus, most functions that you consider are like compositions, composed functions. So a small note, many functions actually are created using composition. That's why it's very important, right? For example, sine, these are basic functions, sine x, cosine x, exponential x, like log x. These are, or square root of x, or things like that. These are like simple functions, but in calculus, if you remember, we considered many functions, not exactly this, but something like e to the sine x, and like x to the cosine x, I don't know. Just we can make many things, e to the x squared plus cosine x log x, something like that. These are actually compositions of functions. They're all created by compositions. That's why it's very important. For example, if we want, just think of this simple thing like log of x squared plus x. What is this? This is composition of two things where, let's say, f equals log f of x, let me be more precise, log of x, and g of x equals x squared plus x. If you compose x, f and g, we get this. So if you have more things, we can compose more and more g and h. We can compose many things, right? So by using composition, you can make our set of functions like huge. Any question? All right. The next one is about sequences and strings. So what is a sequence? It's very simple. It's just a list. Sequence is just a list of objects. Like 1, 2, 3, 4, or I don't know, anything. It can be anything. Not necessarily numbers or letters. Anything can be okay. I don't know. It can be a set or empty set and then 1 and then -1. Doesn't matter. Any object. Sine, cosine x, sine x. Anything can be a sequence. The sequence is just a list of objects. If S is a sequence, then Si denotes the ith element in S. For example, so in other words, S is S1, comma, we will understand a sequence like this. Or we can write this because, you know, it's quite long. We sometimes write this Sn, where n is from 1 up to 1, 2, 3, etc. So this sequence can be represented like by listing this or listing the formula for the nth object. By the way, sequence can be thought of as a function. Sequence, note. Sequence can be thought of as a function. How? So suppose S is a sequence like this. Then S is a function from 1, 2, 3 positive integers to set of object. I don't know. Set of object. Because S1, just think of S1 as a function S of 1, right? So it assigns an object S1 to 1, S2 to 2, etc. So sequence is basically a special function where the domain is the set of integers 1, 2, 3, dot, dot, dot. Sequence is a function. Okay. Sometimes we consider finite sequences, or sometimes we consider infinite sequences. So for example, 1, 2, 3, this is very simple sequence. We can write this as like n from 0 to infinity. We can write this, or, oh sorry, it should be 1. Or like I wrote before, it can be written, they mean the same. 1 to infinity. Or if we have 2, 4, 5, 6, 8, you can write the finite sequence. Here is an infinite sequence. Is 2n, n from 1 to 5, 4. Oh no, what did I do? Yeah. Yes. This is better. Okay. Sequence with 4 integers, the finite sequence. And of course, we don't have to start with 1. Sometimes we consider sequence like Sn, where n is from k to infinity. Let's just say it's from k. Index is from k. This n subscript is usually called the index. Or starting from, usually we start the subscript, the index usually begins with 0 or 1. But we can have a more general situation like n is from 5 or even -2. And of course, we can consider Sn where n is from I to j, which means sequence Si, I plus 1, Si plus 2, up to Sj. So this means this. So, yeah, we need to see some examples. Suppose that S is a sequence defined by this. Sometimes it is defined in terms using recurrence relation or just formula or recurrence. Yeah. Let's just use this first. So S begins with 0. I mean Sn. N begins with 0. So we have S0, S1, S2, etc. Right? What is S0? You just substitute n equals 0. So it's 1 plus 4 equals 5. S1 is 2 plus 12 equals 14. S2 equals 4 plus 4 times 9, 36, 40, etc. In this way, you can compute as the ith element in your sequence here. So you can have an example like this. For Sn as above, show that it satisfies the recurrence relation like this. When n is greater than or equal to 2. It should be 2 here. How can we show this? You know, we have a formula here, just substitute there. So this part, the right hand side, you can just use the formula over here. This is 5 times 2 to the n minus 1 plus 4 times 3 to the n minus 1 minus 6 times 2 to the n minus 2 plus 4 times 3 to the n minus 2, right? Just compute this, right? 2 to the n here. If you combine 2 to the n together, we have 5 coefficient. And here is 6 is 2 times 3, so the coefficient will be 3. And minus, so it's minus 3. And plus, we have 4 times 3 to the n minus 1 here, and it's going to be 5. And 3 times 2, so it's going to be minus 8. Right? And then you can simplify this. 2 to the n minus what? It's minus 3, so it's 4 times 3 to the n, which happens to be equal to, what? Not equal to this. Maybe I made a mistake somewhere. Can you find it? Oh, I see. This is not 4, but yes. Yeah, I made a simple computation. I don't know. It should be plus here, and it is Sn. Sorry about that. Can you find the mistake here that I made? I can't. Here 2. Oh yeah, that's right. Thank you. This must be 2, right? Yeah. So yeah, plus and so actually it's more difficult if you are given just this recurrence relation and find the nth term. So if you know nth term, by showing the recurrence relation is just very simple. You just do the computation. That's the proof. But going backward is more difficult, but we will learn this later. We call this the solving the recurrence relation. But the thing is, if you have a recurrence relation like this with sufficiently many initial conditions, then you can find the general formula like this. We're going to learn that later. Okay, next definition. A sequence S is called a decreasing if Sn is less than greater than the next one. So the next one is smaller than the previous one. So it's decreasing. If index gets larger and then the sequence gets smaller, it's called decreasing. And it's increasing if the other way around. If the next one is, oh no, I wrote the same thing. If the next one is larger, so increasing. And sometimes you want to have inequality here, so it's non-decreasing. Non-decreasing means Si is not this, that means this. Or it's non-increasing if Si greater than Si. I mean for all I, not just for single I, but for all I. So for example, of course there are many increasing sequences. Increasing, right? This is increasing and both increasing and non-decreasing, right? Increasing and non-decreasing, right? -2, -4, -6, what's that? It's decreasing and non-increasing at the same time. What about 1, 1, 2, 2, etc.? It is not increasing. It's a non-decreasing, right? Because it's decreasing. Sometimes it's also called the weakly increasing. Weakly increasing. Also it's called weakly decreasing. The same thing. Or sometimes it's called strictly or strongly increasing. But in the textbook, we're going to use this. All right. And we have many definitions because this first lecture of this section, this chapter, so we need to introduce many notation. So let's say this is a sequence. We have a sequence, I from I from M to N. Then we have this notation, right? Everyone knows. This is the sum of the elements in the sequence, right? And the product is also defined. So we use this very often in mathematics, right? And because manipulating the sum or product are very common, so we need to practice with something. Sometimes we change the index. You can change the index. It's very important to be able to change the index as you wish. You can change the index I in the sum or this or product. For example, summation I from 1 to n, 3 to the I. Here we can say, okay, now I don't want to I don't want I to start from 1. I want the index to begin starting from 0, for instance. So let's say j equals I minus 1, or I equals j plus 1, say. The same thing, right? Then if I is j plus 1, it's going to be j plus 1 like that, right? Then what is the range for j then? If I is from 1 to n, what is the range for j? J is from 0 to n minus 1. They are the same thing, right? So sometimes we change the index like this. And by the way, the index, the letter for the index is not what's important. You can use any letter here. It's going to be I. You can change back to I, the same, or K. Anything can be fine. Except, of course, n, you know, if you have n from 0 to n minus 1, it's confusing. So the index, the letter is not important. Also, we can also change like this. We can also change the index like n minus j, let's say, from here. Then what is the range for j? So I is now replaced by n minus j. What is the range for j? When I equals 1, j equals, here it is the same, j equals n minus I, right? So you may try to write n minus 1 to like 0, but this is not the usual way of writing the sum. So when I is n minus j, j is from 0 to n minus 1, right? Because when I is n, j equals 0. When I is n minus 1, j equals 1, etc. So it's the same. They are all the same. This is equal to this, or they're all equal sum. This is very important because sometimes summation is not exactly the exact form that you want. Then you need to change the index so that you want to make this as the same shape that you want. And also we have a more general summation notation, not just like integer like this, but we can also have more general summation notation. If suppose A is a set of elements like this. If it's a set, then we can also have something like this. I is in A, I. What does this mean? For every element in A, we add that. So this is A1 plus A2 plus ... AN, right? So it's simpler if you know this sum. This is also very common notation. And also, of course, I in A, I is a product of the elements. Of course, they all mean the same thing. Product I from 1 to n, AI is the same. Sometimes this can be more useful. Simpler. Okay? Alright, so the sequences. Oh, yeah, some more on sequences. Suppose that we have a sequence like this. It's a sequence. Let's say n1, n2, ... This is an increasing sequence of integers in m plus 1, m plus 2, etc. So you just select some of them, or infinitely many of them, and then write them in increasing order like this. So that gives us another sequence, right? then you just select those whose indices are taken from here. Ni, I from 1 to infinity, this is called a subsequence of S. Let's say S. In other words, subsequence, so this is a kind of a difficult way of defining it, but the meaning is quite simple. You have a sequence, it's a list of objects like this, so S is like Sm, Sm plus 1, Sm plus 2, etc. Subsequence means you just select some of them as you wish. I'm going to select this, but they must be in the same order as in the sequence, original sequence. That is a subsequence. Basically, that's what this means. So example, 1, 2, 3, 4, dot, dot, dot. This is a sequence S, SA, and 1, 3, 5, the sequence of odd numbers. This is a subsequence of S, right? But like 2, 1, 3, this is not a subsequence of this because they are not in the same order here. So not a subsequence. A finite one can be a subsequence. This is a subsequence. Subsequence of S. As long as they are taken from the original sequence and in the order, same order, then it's a subsequence. All right. Now, let me talk about strings. So strings are really the same as sequences. Let's say X is a finite set of some elements. A string over X is basically a sequence, a finite sequence of elements from X. But you can take one element more than once. So for example, let's say A, B, C. Sometimes it's called string is called a word, and the element X is called a word of the set of alphabets. So, you know, what is a word? Word consists of alphabet, like mathematics. Alphabets are A, B, C, D, as we know. It's just a sequence of alphabet, right? Yeah. The string is like that. Think of string as a word. So if our alphabet or finite set X is A, B, C, then what are the strings? There are infinitely many strings actually. A is a string, B is a string, C is a string. Nothing empty set, nothing is also a string. Think of this. AB or AA, BB, BC, CA. These are strings. There are many strings, infinitely many. A, like a lot of, but each string must be of finite length. And because, you know, it's kind of tedious to write many things like A, and then B, C, this kind of taking a long time and hard to recognize at once. So if these are repeated, we simply write A like a power, B to the fourth C. This notation means we have 5 copies of A and then 4 copies of B, etc. Just a shorthand for this. So like I said, the empty string, because empty means nothing, empty string is also considered as a string. Also considered as a string. And it's called null string. Empty string is the null string. And because this no, let's not use this for here. Denoted just to indicate that lambda, because we want this, this is reserved for the empty set notation. So empty string or null string is denoted by lambda. Okay, just for this is our notation. And let's see some notation. X star is a set of all strings over X. What about X plus? X plus basically is a set of all strings, but we don't want to consider a null string. Set of all strings over X except null string. In other words, X star is, X plus is X star minus the null string lambda. So example X equals say A comma B. Then what is this? There are many, infinitely many. We cannot list them all, but it's lambda. It has lambda null string A, B, A, B, B, A, B, B, A. By the way, A, B, and B, A are different, of course. They are different strings. A, B. There are many, too many to write them all. So many, infinitely many. What about X plus? The same thing except lambda. So A, B, A, like so. Okay, and we have some natural terminologies like length. The length of a string, say, let's denote the string by alpha. What is the length of this string? That's the number of elements there. Is the number of elements, like a length of a word, elements in alpha. And the length is denoted by alpha, like an absolute value. So for example, alpha equals A, B, A, B, A, then what is the length of this? You just count the number of letters there. 1, 2, 3, 4, 5. The length is 5. And beta equals A 10 to the 10, B to the 20, C to the 30. What is the length of B, beta? Let's just add them all. 10 plus 20 plus 30, which is 60. Okay? All right. There are some more definitions to go, unfortunately, but they are natural definitions in some sense. Suppose we have two strings and then we can attach them together. AB, this is the string obtained by concatenating alpha and beta. Is a string by concatenation. Concatenating alpha and beta. So for example, maybe an example is better than this definition, I guess. Let's say alpha equals this sequence, a string, B is this string. What is alpha beta? You just attach beta after alpha. So alpha is ABC, beta is CBA. So this is alpha beta. You can kind of combine strings, because we in mathematics we like operations. We learned strings. We want to make more strings out of old ones. And also in mathematics, when we introduce some kind of notion like sequence, set, things like that, we often talk about something, subset, substring, or subsequence or substring. What is substring? A string, beta is a substring of a string alpha if alpha equals gamma, beta, delta for some strings alpha, gamma, and delta. If we can write alpha, things like this, then beta is called a string. So it must be a consecutive string in alpha. If you can find exactly this beta in your alpha consecutively, then it's called a string, substring. So for example, let's say alpha equals ABC, ABC, and beta equals BCA. Is beta a substring of alpha? See if you can find beta here. Can you find it? Yes, beta is here. So it's a substring. What if I say gamma equals like A, B, A? Is this a substring of alpha? Try to see if you can find ABA by reading alpha here. No, you don't have there. It is not a substring of alpha. Of course, if you A, B, A are there, but they are not consecutive, so we don't think this as a subscript, a substring. Okay. Okay, let me give you some example. X equals A comma B. F is a function from string to string, x star to x star. What is x star? Set of all strings over x a comma b. And how do we define this? It's defined by, the function must be defined, f of alpha equals alpha reverse. Here, AR means the string obtained from alpha by reversing it. You know, reversing alpha, reversing it. So if you have a sequence, just read it backward, then we get again a sequence of alphabet, so it's going to be another sequence. That's a well-defined function. Then, for example, f of A, B, A, what is that? Just read it backward. A, B, A, A. It's like that. So to show that F is a bijection. Bijection means two things, one-to-one and on-to. Proof, one-to-one. How can we show that a function is one-to-one? Suppose that f of alpha equals f of beta. We need to show that alpha equals beta, right? Now, by definition, this means alpha reversed equals beta reversed, right? But let's reverse them again. This means we can reverse this again. What is this? Oh, by the way, because we have the same string, their reverse must be the same. Right? If you have the same sequence, if you reverse them, of course you must get the same thing. But what is this? You have alpha and then you reverse it and then you reverse it again, then what do you get? The original sequence, alpha. And here again, reverse and reverse must be itself. So alpha equals beta. So it's 1 to 1, right? That's done. What about onto? For any sequence, can we find for any sequence, string in X, can we find, is there beta such that f of beta equals alpha? Can you find such beta? So for instance, you have a sequence A, B, A, B. Which string gets sent to this by F? Just reverse it, right? Because we know, yes, beta is, take beta to be alpha reverse, right? Then F beta is beta reverse, but F, this is alpha reverse, and reverse is alpha. We just found it. So it's 1 onto. So it's 1 to 1 and onto. Any question? Let me do one more example. F, again, X is A comma B. F is a function X star times X star to X star, where F alpha comma beta is defined to be concatenation. Okay? So we have a pair of words or strings, alpha comma beta, then we just concatenated it. It's a function. It's a well-defined function. Is this 1 to 1 or 1 to? Do you think it's 1 to 1? 1 to 1 or not? So 1 to 1 means can you make this string by different way by finding two different alpha beta? Can you do this? Yes. How? Just give me an example. Like AAB. This can be obtained by concatenating AA and B, and also A and AB, right? This is f of the same thing, A comma AB or AA comma B, but they are different. So it's not 1 to 1. No. And onto? Is this onto? Can you always write something as a concatenation? Yes, because we have the empty null string. Any alpha is lambda alpha, which is f of lambda alpha. So yes, we can always find this. Yes. So it is not 1 to 1, but it is onto. So these are, if you understand the definitions, these are not difficult things. But yeah, this will be helpful to make this concept more understandable. All right, let's finish today's lecture, and thank you for your attention.